Okay, so looking at our examples, remember we're looking at these molecules and looking for molecules which might be chiral molecules, molecules which have a mirror image molecule with a non-superimposable mirror image, non-superimposable, and therefore giving us two unique molecules because of unique spatial arrangements of the atoms. The easiest way to find a molecule that's going to have a non-superimposable mirror image is one that has four unique groups attached. So we can discount any terminal carbons because they have three hydrogens attached. That is in four unique groups. There's three hydrogens which are exactly the same. We can discount any carbons which have two hydrogens attached. So any secondary carbons again with two hydrogens, they are out to gain. I'm really looking for tertiary or quaternary carbons if they have four unique groups. So there's only one hydrogen here, but it does have two identical methyl groups, CH3, CH3. So that's not unique. So there's nothing unique on this molecule. Second molecule, we've got three hydrogens here, two hydrogens here, so we discount those. Then with one hydrogen, there's a 1, 2, an ethyl branch to the molecule to the left. There's a hydrogen which isn't shown, a bromine, and then a 1, 2, 3, a propyl branch with a methyl branch on that. So there are four unique groups attached. So this is a chiral carbon, a stereocenter. And normally we'd represent that with a little asterisk next to it. I don't have a pen, so I can't do that. Well, why do people keep pencils all the time? Pencils are useless. Pen, that's what you want. So, asterisk next to the carbon atom there. Next carbon, we have got two hydrogens, so we discount that. And then here, there's only one hydrogen. Again, there's two identical methyl groups. All four groups have to be unique. So no chiral carbon there. But we do have one chiral carbon, so this does make for a chiral molecule. We'll have a mirror image, which is non-superimposable. Third molecule, three hydrogens here, and on the line, two hydrogens each time, except for the hydrogen here. But we do have, because of that cycle, we have identical chains spawning around that cycle. From this point we see CH2, 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 and we see the exact same linkage, the exact same train of carbons around the other side. So although they're linked, they are actually just identical. We can also see that the molecule is highly symmetrical, which is another giveaway for lack of chirality in the molecule, when there's a symmetrical aspect. So no chirality of that third one. The fourth one, again, any terminal carbons with three hydrogens we can discount. Any secondary carbons with two hydrogens we can discount because we want four unique groups. Carbon in the middle does have just a single hydrogen attached. We've got an amine group, but we've got two identical ethyl groups. Again, there's symmetry down the middle of the molecule. Two ethyl groups, it's not unique, so there's no chiral center. And the last molecule, again, discounting terminal carbons, discounting secondary. So the interest comes from the carbon here and the carbon here. We do have unique groups attached. We'll look at the sequence, the connectivity from this point in the chain. That carbon has a ethyl group attached. It has a hydrogen attached at that point. And if we go clockwise round the ring, we see, or extend this out, we see a CH2 group, and then we see another CH2 group, and then there's a CH, Cl group, then a CH2, and then back to the starting point. Now if we go counterclockwise, anti-clockwise around the ring, we see a CH2 group, so no difference there. But then we see the CHCl group at an earlier point in the chain. Or going clockwise round, we don't see that to the 1, 2, 3rd carbon. Here we see it on the 1, 2, the 2nd carbon atom. So spatially, if we were trying to superimpose a mirror image molecule, the chlorine atoms would be sticking out at different parts of the sequence. So although we see in total the same total number of carbons, hydrogens and chlorines, we see them in a different order, in a different sequence. And there's a CH2 group, then almost back to the ring there's another CH2 group, and then we get back to that starting point again. We see groups, we see atoms at different points in the chain sequence. So that does give us chirality at that point. Chiral carbon. And likewise, when we are looking at this carbon in the chain, if we go clockwise, we go 1, 2 carbons to get the ethyl branch. But from the other side, anti-clockwise, we go 1, 2, 3 carbons to see that ethyl branch. So those FO branches wouldn't be able to be superimposed on top of each other because they're occurring at different points in the sequence. So it's again giving us a unique 4 attachments to that carbon. So there's a second chiral center on the molecule. Molecule 2, molecule 5 are the 2 examples of chiral centers and our chiral molecules. Okay? So these molecules will be chiral. Rubbish transfer. Yep. Oh, there's a bit. Yeah. So look for stereo centers, therefore molecules which should be chiral. So we're looking for unique attachments. Again, any carbon that has more than one hydrogen cannot be chiral. We're looking for 4 unique groups. So through the 2 atoms in the middle here, they look promising. We've got a CH3 group coming from this carbon, there's a bromine, there's a hydrogen, and then there's CHBr, and CH3. Here's a potential problem. Look on the other carbon, it also has a CH3 group, there's a Br, there's a hydrogen, and a CH, Br, CH3. There's internal symmetry in this molecule. We can create a mirror image plane. Remember, these bonds are free rotating. We can twist it around and look at the other half as an internal mirror image plane. So although we have individual chiral carbon atoms, the molecule itself will be achiral. Chiral carbons, because they have 4 unique groups when we're looking at that specific point, the entire molecule is achiral because of the internal symmetry of the molecule. About any primary carbons and any secondary carbons, it's all about tertiary and quaternary. So we've got a methyl group, a bromine, a hydrogen, and 1, 2, 3, 2 bromo-propyl group coming off from this position. So that's definitely a stereocenter chiral carbon position. Likewise with the one here. There's a stereocenter, a chiral carbon position. We're running into the same problem. There's an internal plane of symmetry through that molecule, which means that although we have stereocenters, the molecule is again achiral. Two mirror image molecules will be superimposable on top of each other because of that internal plane of symmetry. For this one now, again, forgetting about primary carbons and secondary carbons. The tertiary carbon here has only one hydrogen, but it has 2 identical methyl groups, so that's not really anything of interest. The carbon here has a 1, 2 ethyl group and a 1, 2, 3 propyl group of a branch. There you need a hydrogen coming off, and then this cycle butane. So, 4 unique groups attached. There's no internal symmetry in the molecule. Carbon here, if you look at the 2 branches around the ring, CH2, 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 and we see the same conformation, CH2, CH2, CH2. So no chirality there, it's just in that carbon there. So that is a chiral molecule. Next one, secondary carbons, CH2, 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 CH2. Nothing of interest there. Potentially of interest here at the carbon, it has a hydrogen and a chlorine. We see the same groups in the same order. Whether we go counterclockwise or clockwise, we see CH2, CH2, CHBr, CH2, CH2. So as we go around the ring, we see the same sequence of atoms in the exact same order, regardless of which way around the ring we go. Same from this position, same sequence of atoms seen as we go around the ring. So, non-chiral. Last one. Again, the secondary carbons are not of any interest because there's double hydrogens on this position. The bromine atom here has 4 unique groups attached. As we go around the ring in a different order, we see these branches in a different part of the sequence. So if we're going clockwise and counterclockwise, you see CH2, CH2, you see CH2, CHF. We're seeing the atoms in a different order. And CH2, CH2, CHF. We're seeing that fluorine branch in a different part of the sequence, depending upon which way round the ring we go. So they are 4 unique groups. This is the chiral position. Likewise for that carbon atom there, that's also a chiral position, because as we move around the ring, either clockwise or anti-clockwise, which is related to counterclockwise, CH2, CH2, CHBr, CH2. So we're seeing that branch in a different part of the sequence. So when we try and superimpose those molecules together, remember it means that we're trying to get the bromine atom to be on top of the bromine atom in the mirror image, and the fluorine atom on top of the fluorine atom in the mirror image. They're going to be occurring at different parts of the chain. They're not going to be spatially at the same point. Okay, so